Welcome to a Let's Tinker edition of the DC Current. I'm your host, Damon Caskey, and this beautiful piece of artwork I'm sitting astride is the Outlaw. Before I get started on anything else, I want to apologize right away for any of the wind and automotive noise. I realize now I probably couldn't have picked a worse spot. I'm hoping this new Bluetooth mic will ameliorate that just a little bit, but I cannot be certain because I've never tried it before. Also, before we move on to the topic, the actual topic at hand, a quick history lesson. This bike's name, the Outlaw, actually comes from its late owner's series of race cars. Tom used to run dirt track, he ran drag cars, and he also ran Daytona Dash. And in almost all cases, his cars were christened Outlaw. This name was the mascot of a restaurant some of you long-term Ashland, Kentucky residents will remember called the Outpost, that once sat at the corner of Route 5 and Route 23. You will now find a McDonald's there. I guess it is what it is, but quick history lesson there. Now let's move on to the actual topic. A few days ago, I posted this melodramatic tweet about my kingdom for objective class support. And of course, most people didn't have any clue what I was talking about. Some of them actually asked, and I love the curiosity, so thank you all. I tried to explain through text, and no surprise there, because it seems I'm not very good at expounding through text. The meaning just didn't come across very clear, and believe me, that's not the first time. So I figured, why not just go ahead and make a recording out of it and explain from start to finish the difference in between procedural and objective-oriented programming. This bike here is going to help me do so. Now, I'm sure you're wondering what in the world a motorcycle has to do with computer programming. Very simple. I introduced myself as Damon Von Caskey, but my full name is Damon Von Caskey, and I introduced the bike as the Outlaw. Those two things have something in common. They are properties that belong to entities. I am an entity, as is this bike, and we both have properties, as does pretty much anything else you can think of. Some of these properties are unique, some of them less so. For example, we can take the bike, and going from most unique to less unique, we would say this bike is a black-on-white color, fat boy, soft tail, Harley-Davidson, two-wheeled motorcycle configuration. Using myself, I guess I would say Damon, my first name, middle name Vaughn, last name Caskey. Then let's just go ahead and skip a few right on up to my species, Homo sapiens sapien, kingdom, Animalia. All those things are fairly static. In some cases they can be changed, like the name, for example. In some cases they can't. I certainly cannot decide that I have a new species, and we can't change the model of this bike unless we're lying about it. Some properties, of course, can. I think I already said that, excuse me. There are also actions that the entities can take. In the bike's example, its most basic actions would be start, turn, stop, arc. In computer terms, we would actually have to write code, of course, to make all these things happen. So let's start with first a property, and then we'll move on to an action. The property we'll use is color. Now, you and I can both take a look at this bike and say, okay, it's black trim, white background, it's black on white, it's a white bike. A computer, of course, cannot do that. We have not reached the level of AI distribution yet where any reasonable program is able to perform that type of abstract analog thinking. You can only make Boolean comparisons. So what that means is, you would take part of this VIN number here that actually has a color code, and then you would compare it to a series of information in a table. This table could be a hashed array, it could be something like an Excel sheet, it could be a database, or it could just be static code written right in. Just as an example, I'm going to throw up some static code on screen that will show you exactly how this comparison works. As you can see, this switch statement takes an input and compares it to a couple of different options. When the computer discovers the matching option, i.e. the matching number, and this matching number is found through Boolean comparisons, it then extracts the attached information and sends it back to the user. A very, very simple procedural function. we'll call it get bike color. Here's where things start to go awry though. In the real world, that simple function would be patently useless. First of all, it has no way whatsoever to get input from the user. It has no way to actually truly send output to the user. I mean, I put a return on there, but return what? Return where? We've got to find some way to get it out to the screen, or out to a printer, or more likely, out to a larger part of another program. Excuse me, out to a part of a larger program. I've lost my power of speech today. So, that function is going to require a lot of code to actually operate. And it also needs some error checking. What if the user puts in a value that we didn't anticipate? In the best case scenario, you're going to get an erroneous value sent back out to the user, or nothing at all. In the worst case, you get a bug or a good old-fashioned crash. And if you've ever used a computer, you've seen the results of erroneous inputs, because that's usually that or a divide by zero is what's killing your machine when it goes into a crash or a lockup. We obviously want to avoid that. We'll leave the lack of error checking to the folks up in Redmond, West Virginia. Up to the folks in Redmond, Washington. So, we put together our function. We add the code that actually makes it work. So we've got, we'll just guesstimate anywhere from a 15 to 20 line function, all just to get the color of a bike. And that is assuming that we didn't need any type of code to bring information down from a database. I'm just using a static example that, again, is not very likely to work in the real world. This really isn't much of a problem all by itself until we have to start getting other properties. What if we want to get the model of the bike? Well, now we have to write a nearly identical function. It has to have all of the same error checking. It has to have all the same input, all the same output extrapolation, which means a lot of copy and pasting. Now you're probably thinking, well, who cares about copy pasting? I do that in Word every day. Well, that's all well and fine, but in code, that's really bad. We call it copy pasta, and when it starts getting errors in it, then it's then referred to as code smell. We don't want these sorts of things. If nothing else, it's just hard to edit. What happens if, say, the error message we send to our user when they give us bad input, we decide that we want to put something else. Maybe we want to switch languages. Well, now we've got to go to every single function we wrote to extract every single property for this bike and edit it all by hand. Or we can try a a find and replace and hope that it doesn't mangle up our code. Not a really great way to do things. So there's a couple of different techniques that try to get around that problem. First is we spider our functions together with injected dependency. What that means is you could take a smaller function and have it actually act as the interface to the user, get bike color, and then it works by sending a parameter to a larger function that actually does the work, and then that larger function contains all of our copied code, the error checking, the input, the output, and so on and so forth. That's well enough, but then that winds up having the issue that I talked about in my tweet. To make that efficient, you've got to have large enum lists, or large lists of defined constants. They're both essentially the same thing. What these are just larger versions of that switch statement I used as an example to tell the function the work that actually needs to be done. That's all fine and dandy, but when you wind up with, let's say, 70 or 80 properties instead of just 10 or 12, then the enum statement itself becomes a problem. It gets disorganized, and you're back to having copy pasta and code smell all over again. There's a couple of other techniques you could use. One of them involves global variables. The reason why that's a bad idea is way beyond the scope of this particular video, so I'll leave that alone. Well, let's move on to actions. Now, actions are very similar to properties. All we really do is just conduct an action. Instead of sending values out to the user, we actually tell the code to perform some type of work. In this case, again, using the bike, instead of asking what color the bike is, we tell the bike to start. It's no different than me pushing the start button on the bike here to fire up the engine. So pretty simple, same principle, same problems as the property getting methods. How do we solve all of that? How do we get rid of all of that code mix? I mean, after all, what happens if you want to write a highway program and you don't really care how the bike works, you just want to put a bike on the road? That's kind of like, I guess the best real-world example would be, most of you out there, I'm sure, don't care at all about spark timing. You don't give two spits about the 7-to-1 fuel mixture optimal ratio. You don't care about the final drive of your of your differential, excuse me. You don't give two spits how the transmission works. And forgive me for losing my power speech 15 times here. All you want to do is get in your car, turn the key, and drive it. Well, as programmers, we kind of want to do the same thing. If I'm writing a program about highways, I really don't care how the bike portion works. If I don't have to write it, that's wonderful. This is where object-oriented programming comes in and where it really shines. Object-oriented programming basically takes those verbs and those nouns and makes them real, that makes them part of the program. So we take all of our functions that we use to extrapolate this information. We take all of our functions that perform actions, and we put them into a code block that we call a class. For instance, we'll take all this for our bike and we'll put it inside of a class that we call bike. Now again, it's just a group of code. We still had to write the functions to do the work. We just didn't have to copy as much code because we could put a lot of the variables inside the class and transfer it back and forth. Now, I'll leave that portion for a more detailed article later on. But let's just say we take the code smell and we hide it away. Once we've got that ready, we can then initialize that class as an object, and that object goes inside of a singular variable. So, once I have my class, my bike class, I initialize that bike class as X. And I'll put that on the screen real quick as an example. So you can see, I define my class over here, I put my code inside of it to do the work that I need done, and now I initialize X. And once I have X, I say X color, and I get the color. I say X start, and the bike starts. I say X model, I get the model, so on and so forth. This does a couple of different things. First is it gets all of that code mess over here into one space, and then lets us organize that code as we see fit. We can transfer variables inside of that class without them being global to the whole program. That way we don't have to have so much copy pasta between the functions. Whatever functions we put inside that class are now available as what we call methods outside the class, i.e. the method start, or the property white, the property color, that is white. And in our main portion of the code over here, that I'm going to put up on the screen again, you can see that it's much, much, much cleaner. I don't have to see any of that copy pasta anymore. Now this is especially handy, again, if I'm wanting to write a larger program about, say, highways, and I don't care how the bike works, I'm just going to put the bike on the road. So all I do is take this class file that I may have written earlier that someone wrote for me, and I initialize it, and then I can do whatever with the bike is available. And the last thing that I probably should have mentioned up front, all of those functions take parameters to work. So remember, when I said I wanted the bike, I wanted the bike's color, and we had our get bike color function, we had to put a parameter in it that actually sent it the VIN number here. Well, if I ever decide that I need to put more functionality into that, like let's say I want details about the bike's color, then I would have to put more parameters in. That function is no longer compatible with anyone who ever used the program before. With our class file, we don't have that problem anymore. we can update portions of our class file, and the portions outside of the class file will work just fine and dandy. So for example, if I decide to put in the ability to turn on the headlight inside of the class file, all I have to say is X headlight on, and my X start bike still works. Those are units of class files. That is why I was complaining about the limitations of C programming, which I was stuck with, as compared to C++ programming, which does in fact allow object-oriented. Now, comparing languages is beyond the scope of this article. All I really wanted to do was explain procedural versus OOP. I hope I've managed to do that for you, and if you have any questions, by all means, throw them at me, and I'll be glad to answer them as best I can. This is David Caskey and the Outlaw, signing out from the DC Current. Thanks for listening, everyone, and we'll see you next time.